always been about one number: net gain. For decades, fusion experiments have demonstrated the ability to generate plasma hot enough for fusion reactions. But sustaining those reactions while producing more energy than consumed has remained elusive. Helion's Polaris reactor attempts to change that. Unlike traditional tokamak designs that rely on continuous plasma confinement inside large donut-shaped chambers, Polaris uses pulsed magnetic compression. Two plasma rings are formed at opposite ends of a linear chamber. Powerful magnetic fields accelerate and compress them toward each other. When they collide, temperature and pressure spike. If conditions are sufficient, fusion reactions occur. This approach reduces the need for enormous containment structures. Instead of holding plasma in a steady state for long periods, Polaris focuses on rapid compression cycles. Short bursts, but compression costs energy. To achieve fusion, plasma must reach temperatures measured in tens of millions of degrees. Magnetic systems must generate immense field strength to contain and compress the plasma without letting it touch chamber walls. If plasma contacts material surfaces, energy dissipates instantly. Magnetic confinement is the first constraint. Plasma is unstable. It writhes and shifts under electromagnetic forces. Small instabilities can grow rapidly, disrupting compression symmetry. If the plasma becomes unstable during the pulse, the fusion reaction weakens or fails. Precision timing becomes critical. Polaris operates on pulsed cycles, meaning energy is injected into the plasma, compression occurs, and the reaction phase is brief. The system then resets and repeats. For net gain, the energy produced during fusion must exceed the energy used to create and compress the plasma. That is the second constraint: input versus output. Magnetic field generation requires significant electrical power. High current systems drive the compression process. The entire cycle must be efficient enough that fusion output compensates for electrical input. Helion also pursues direct energy conversion. Instead of converting fusion heat into steam to spin turbines, Polaris aims to convert kinetic energy from charged fusion products directly into electricity using magnetic induction. This bypasses thermal conversion losses. In theory, direct conversion improves efficiency. In practice, it requires precise control of particle motion and electromagnetic capture systems. Plasma temperature is not the only variable. Fuel selection matters. Helion focuses on advanced fuel cycles that produce charged particles rather than large neutron flux. Neutrons damage reactor materials over time. Reducing neutron output extends system lifespan and reduces shielding requirements, but advanced fuel cycles demand even higher temperatures to ignite. Higher temperature increases compression requirements. Higher compression increases energy input. Higher energy input tightens the margin for net gain. Everything returns to balance. Thermal management also becomes critical. Even if direct energy conversion captures a portion of fusion output, structural components must survive repeated high-energy pulses. Material fatigue accumulates. Reactor components endure rapid electromagnetic stress cycles. Structural design must handle repeated compression events without degrading performance. And then there is scaling. Small prototypes can demonstrate proof of concept. Scaling toward commercial output introduces new constraints: continuous operation reliability, maintenance cycles, grid integration, and cost control. Fusion is not limited by fuel availability. It is limited by engineering. The physics of fusion are well understood. The sun proves that. The challenge is achieving those conditions economically and repeatedly on Earth. Polaris represents a shift toward compact systems rather than massive infrastructure. That reduces construction scale but increases precision requirements. If magnetic compression is imperfect, energy is wasted. If plasma instability grows too quickly, reactions collapse. If energy input exceeds fusion output, net gain disappears. The equation is unforgiving. Fusion has been described as the energy of the future for decades. Polaris attempts to move that future closer by reducing scale and simplifying conversion. But it cannot escape physics. Plasma must be hotter than the core of the sun. Magnetic fields must confine matter that wants to explode outward. Energy input must remain lower than energy output. The promise of fusion is immense. The constraint is relentless. Because fusion is not about starting a reaction, it is about sustaining gain.